Welcome back. We're going to take a look at Unit 1, Lesson 2. I can determine and create equivalent fractions by generating simple equivalent fractions. Simple equivalent fractions. Okay, first of all, I'm going to show you that by using fraction bars like we just talked about. If you're not sure what a fraction bar is, you'll probably figure it out from this, or you'll have to look at a previous lesson. All right. Here's a fraction bar, that's one whole. If I partition it into two equal parts, my denominator is 2. It takes 2 parts to make a whole. It's the name of my parts. They're halves. All right? If I'm going to look at one of those parts, that's my numerator, 1/2. Now, equivalent to a half. All right? I take my same whole, now equivalent to the half. Well, if I, what we call 2-split, if I split each half into 2 parts, I now have 4 parts to make a whole, so each part is 1/4. Well, how much was that half? Probably should have shaded it beforehand. That 1/2 became 2/4. There's some interesting things that you should recognize here. My denominator got twice as large, making the pieces half the size, or twice as small, we might want to call it. So my pieces got twice as small, so I needed twice as many pieces to be what's called equivalent, or equal in size. So as my denominator got twice as large, the number, meaning the parts got smaller, I needed twice as many. Now, let's take our half again. What's another fraction equivalent to a half? And usually students know these pretty well. 1/2 is equivalent to 2/4. Well, if I partition these into 3, if I 3-split each half, and remember I have to do it all the way across because I need to make all of my pieces equal in size. I now have 1, 2, 3, 4, 5, 6 pieces, so my denominator is 6 to make a whole. Each piece is 1/6, and 1/2 is 1, 2, 3, 6. Let's take a look at one more using the fraction bars. Taking halves, 1/2, and I'm sure at home you can think of a whole bunch of different fractions equivalent to a half. Let's go with, if I partition this into eighths, we'll just do the next one, eighths. So if I partition each piece, right now it's 1/2, into fourths, then eighths. I 1, 2, all right, I 4-split it. I cut it 1, 2, 3 times to make each piece into 4 pieces. So now I take 8 equal pieces to make the whole, so they're eighths, and I have 1/8 plus 1/8 plus 1/8 plus 1/8, 4/8. Now, mathematically, I don't necessarily want to keep drawing fraction bars, especially when we get more complicated fractions. So mathematically, what can I do to change these? What changes 1/2 to 2/4? What changes 1/2 to 3/6? What changes 1/2 to 4/8 without changing the value? what can change these without changing the value? Well, when I think about operations that I know that multiplying by 1 does not change the value of a number. 1 multiplied by 3 is still 3. 1 multiplied by 10 is still 10. 1 multiplied by a half then is still going to be equal to 1/2. So we're multiplying by 1 in the form of a fraction. So what fraction form of 1 gives me 2/4? What times 1 gives me 2? 2. What times 2 gives me 4? 2. And 2/2 is 1/2. What times 1 gives me 3? 3. I shouldn't say times, I should say multiply. What 2 multiplied by what gives me 6? 3. And 3/3 is 1/2. 1/2, what fraction equal to a whole is going to give me 4/8? 4/4. So what this shows you is to make an equivalent fraction, you multiply your fraction by 1 in the form of a fraction. Where your numerator and denominator are the same number. Now, I want to show you another way to model fractions other than a fraction bar. Another way to model fractions other than a fraction bar is a number line. And number lines work really well when we start getting into mixed numbers. I'm only going to use part of a number line, so I'm not going to put arrows. I'm just going 0 to 1/2. I think what we're going to represent in my number line, I partitioned it, I made 2 cuts. That partitioned into 1, 2, 3 equal pieces. So I've partitioned it into thirds. 1/3, another third would make 2/3. 1/2 is 3/3. All right. So let's take a look at 1/3. All right. Equivalent to 1/3. So if I take my 1/3 and I 2-split each third. Oh, hold on. Let's take our 1/3. I take my 1/3 and I 2-split each third. 2 pieces, 2 pieces, 2 pieces. I now have 6. 1, 2, 3, 4, 5, 6 pieces. Make each piece a 1/6. So my 1/3 is now equivalent to 1, 2, 6. Let's look at our multiplication theory that we came up with a minute ago. 1/3 multiplied by 1, I 2-split it, so I'm going to multiply it by 2/2 because my 1 became 2 pieces, it got multiplied by 2, and so did all 3 of them. Each piece got 2 times smaller, So I need 2 times as many. And 1 multiplied by 2 is 2, and 3 multiplied by 2 is 6. It worked. Now, let's try it again. 0, 1/3, 2/3, 3/3. And I have 1/3. So I'm taking 1/3, and this time I'm going to 3 split it. So I'm going to 3 split the 1 to make it into 3 parts. That's 2 cuts to 3 split it. Now, I don't have all equal parts across my fraction, or across my whole. So I have to 3 split everybody else. And remember, 2 cuts, 3 split them into 3 parts. Now, my 1/3 became 1, 2, 3. And it takes 1, 2, 3, 4, 5, 6, 7, 8, 9 to make a whole. 1 multiplied by 3 is 3. I have 3 times as many pieces. 3 multiplied by 3 is 9, but each piece is 3 times smaller. So that's why multiplying by 1 gives me an equivalent fraction. I have more pieces, but the pieces are smaller. The larger my numerator, the more pieces I have. The larger my denominator, the smaller the pieces. Okay, so that's using a number line to represent a fraction. Now, there is another way to make equivalent fractions. Well, actually, first of all, let me tell you, why would I do that? Why do I need to be able to make equivalent fractions? Well, here's why. Let's say I have 1/2 plus 1/3. I'm going to want to use, before I can add these pieces, the pieces are going to need to be the same size. Whoops. There's my 1/2. And there's my 1/3. I can't add these pieces. I could say I have 2 pieces, but what size are they? They're not halves, they're not thirds. Using equivalent fractions, I can take my 1/2 and 3 split each one to make 6 equal pieces. 1, 2, 3, 4, 5, 6 pieces. 6. And remember, so I 3 split this one, and now I'm multiplying by 1. And I have 3, 6. And my 1/3, I can 2 split each one. Remember, 2 splitting makes 2 cuts to give me 6 pieces. 1, 2, 3, 4, 5, 6 equal pieces. And my 1/3 became 2 because the pieces got twice as small. I need twice as many. And now I have equal sized pieces. I have 1, 2, 3, 6 plus 1, 2 more 6 take me to 5, 6. So that's why one of the reasons we need to make equivalent fractions. Now, those fractions are, and I'm not so sure if this is a word, but we call it unsimplifying. It's not the simplest way. 1/2 and 1/3 is the simplest form. How do we simplify a fraction? Well, check this out. let's say I had, this is my number line, here's 0, here's 1. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I'm going to rewrite 1 as 12 12s. So here I have 12s. And I'm going to say I have 1 12, 2 12s, 3 12s, 4 12s, 5 12s, 6 12s, 7 12s, 8 12s, 9 12s. So, how can we simplify 12s? Well, if multiplying by 1 doesn't change a number, what else doesn't change a number? That's right. Dividing by 1 does not change the value of a number either. So if I divide these by the same number, I'm not going to change the value, or the numerator and the denominator by the same number, I'm not going to change the value. The tricky part is, what can I divide both 9 and 12 by? I can multiply everything by something. Every number can be multiplied by something, but I can't evenly divide 9 by every number. So what's something I can divide 9 by? Well, I can divide 9 and 12. What's something I can divide them both by? I can divide them both by 3. So I'm going to divide by 1 in the form of 3/3. So 9 divided by 3 gives me 3. And 12 divided by 3 gives me 4. So my 9 that were circled became 1, 2, 3 circled. And my 12 that were circled became 1, 2, 3, 4. The size became 4s. So 9 twelfths is equivalent to 3/4. I what's called simplified by using a divisor of 3 and 3 for my numerator and my denominator. I divided them both by the same number. I get equivalent fractions by multiplying by 1 or dividing by 1 in the form of a fraction. I thought I'd show you this one more time. So I made another number line. Let's see what it represents. All right, it represents 1, 2, 3, 4, 5, 6, 7, 8. So my numerator is 8. And my denominator is how many it takes to make a whole. So it takes 9, 10, 11, 12, 13, 14, 15, 16 pieces to make a whole. Some of you might remember what that's equivalent to. But let's take a look at how we can mathematically find it. All right. So we have 8/16. What's something I can divide both the 8 by and the 16 by? Well, I can divide them both by 2. Dividing by 2 means how many 2's are in there. So let's take a look. Well, there are 1, 2, 2 2's, 3 2's, 4 2's in there. 8 divided by 2 is 4. That's correct. Now, These pieces, though, that are circled green are bigger. So how many does it take to make a whole? It takes 1, 2, 3, 4, and then 5, 6, 7, 8. And 16 divided by 2 is 8. Now, what else could have my 8 and 16 been divided by? 8 and 16. Wait a minute. 16 is a multiple of 8. I can divide 16 evenly by 8. And I can divide 8 evenly by 8. So what I could have done is said, how many 8s are in 8? Well, in 8, there would be 1 8. And in all of the 16, how many 8s are there? There's 1, 1, 2, 3, 4, 5, 6, 7, 8, 2 8s. I realized I kind of skipped one. Another thing I could have done is divided both of them by 4. I could have taken my 8/16 and divided it by 1 in the form of 4 4s. How many 4s in these 8? There is 1 4 in those 8s. How many 4s are in all 16? 1 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4 4s. Sorry, there's 2 4s in 8. So, in simplest form, this is called simplest form because they can't be divided anymore. These could both be divided by 4 again to get me 1/2. These can both be divided by 2 again to get 1/2. The key is to make an equivalent fraction, you're going to be dividing by 1 in the form of a fraction or multiplying by 1 in the form of a fraction. All right, I hope you enjoyed this. Go ahead and make some equivalent fractions by multiplying by 1 or dividing by 1.